We are going to present here a new method, and that's going to be a very slight modification of the previously defined explicitly forward time-centered space method, which is this one. And as we have seen, this is an unstable method, so it's in principle it's a useless method. So in this method, which is called the lax method, simply what we are going to do is we are going to replace the unj term, this term here, which arises from the time derivative, from the finite difference representation of a time derivative, which is connecting these two values, by its average, by this one. So you are going to make by this replacement. So here basically you have the average of the u values which are located on the left from this one and on the right hand side from this one in the x-axis at the same j time. So we are going to make that replacement, which is actually we are making that by hand. Actually, there is in principle there is no clear mathematical reasoning of doing that and why it should work. And simply doing that, the finite difference representation we're getting within this lax method is the one we have here. So the next thing we are going to do is that we are going to analyze the stability of this method. And you know that this is very straightforward. We're going to use again the Fourier method, which basically means that we are going to replace the u evaluated at nj by this function, the eta function to j exponential a k delta x. So a k delta times n. So we are going to do that replacement. And doing that, this is the expression we have. We are going to simplify it as much as we can. So as you can see, this eta 2j disappear here. It disappears because it appears in all the terms we do have in the expression. Then this exponential also you can simplify it by this exponential. So doing these simplifications, that's the result that we have. And we can simplify it further because this, we already know that this is 2 times the cosine k delta x, and this is 2 times I sine k delta x. So this 2 is simplified with this one, and the same happens with this 2, and we are getting this expression for the this eta function. Just remember this beta, we're going to call, in order to simplify the expression, we're going to call beta this c times delta t over delta x. Now we have to check if this is actually, because in order to be stable, we know that the modulus of this eta function has to be lower or equal than 1. So that has to be clarified and be analyzed. So that's what we are going to do next. And so this is a complex number again, so we do know how to calculate the complex number, the square root of the square of this one plus the square of all this is what we have. We are going to simplify it further because we're in order to make easier the analysis. So we are going to take this trigonometric identity of the square of cosine plus the square of the sine. It's equal to 1, so you are going to substitute that this one, by 1 minus the square of the sine of k times delta x, and doing that and collecting the same group, these two signs, this is the expression we have. So in order that to be lower or equal than 1, you can see that this one has to be lower than 1. And as we know that the maximum value that the square of the sine we can get, it's actually 1, then we have that this one has to be lower or equal than 1. And in order to get that, in order for that to be lower or equal than 1, we need that the square of beta has to be lower or equal than 1. And basically means that the beta, which is positive, has to be lower or equal than 1. So that's actually the condition that we are getting the requirement that both delta x and delta t has to satisfy just was connected with this C parameter in order to the method, this lax method, to be stable. So C times delta t over delta x has to be lower or equal to 1 in order for the method to be stable. And actually that condition is it's quite well-known condition numeric in the finite difference representation methods, and it's called the Courant-Friedrich-Levy condition. So RISC has to satisfy a connection between both time step and the space step in order the method to be stable.